Hello, my name is Angelica Coriano. This is my video submission for lab number 9, shift registers for CET 2114C for digital systems. The submission is for Professor Evans. It's going to include parts 1 and 2 of the lab with the timestamps being in the description box below. Beginning with part number 1 right now. Beginning with part number 1, this is a circuit we were tasked with building, which is a Johnson counter. It involves using D flip-flops to create a continuous counter with the inverse output being the input for flip-flop A. And this is the switch right here, which I'm going to explain how it's built right now. So this is my circuit here. I have two 7474 IC chips, which are D flip-flops. Connected on this breadboard, which is the second breadboard, which works a little bit better. I have a 5-volt VCC going to the positive rail and a ground going to the ground rail, and they're both looped on both sides. For both IC chips, pin 14 is connected to the positive rail and pin 7 is connected to the ground rail. All the clears for both flip-flops, well, both chips and all 4 flip-flops are connected to switch 1. So pin 13, pin 1 and pin 13 for both chips are connected to this row right here, which is connected to switch number 1 so that it can be cleared. And then we have the clock signals connected to the logic switch. So logic switch A is connected to this row, and the clock signals, which are in pins number 3 and 11 on both chips, so 3 and 11 on both chips, are connected to this row that is connected to the logic switch. The inverse output of the last flip-flop, or flip-flop D, is connected, which is pin number 8. It's connected to pin 2 of the first chip. So pin number 8 of the second chip is connected to pin number 2 of the first chip. That's the inverse output, is being the D1. And then Q2, which is pin number 9, not Q2, Q1, which is pin number 5 on the first chip, is connected to pin 12 on this first chip, and that is D2. Q2, which is the output of the second flip-flop on this chip, is connected to D1 on the next flip-flop. So pin 9, which is Q2, second output of the second flip-flop, well, the output of the second flip-flop, is connected to the input of the third flip-flop, which is pin 2 on the second IC chip. And then the output of the third flip-flop, which is pin 5 on this one, is connected to pin 12 on the second chips because it is the input for the fourth flip-flop. And all outputs are connected to these LEDs. From left to right, it is pin 2 for D1, not pin 2, pin 5 for Q1, connected to the LED number 3, pin 9 for Q2, connected to LED number 2, pin 5 again, but on the second IC chip, connected to LED number 1, which is it's the white cord right here, it's a white wire, and Q2, the output of the last flip-flop, which is pin number 8, is connected to LED 0. That is how this circuit is wired. So I'm going to move on to the first section that states toggle the clock switch several times and then move it to the 1 Hz clock signal. So I'm going to turn this on, and I'm going to clear my circuit because it is an active low clear. I'm going to put it back on high so that I can use it. So I'm going to toggle. And with the Johnson counter, the ones come in and then disappear. And that is it with the logic switch. I'm going to turn the circuit off. I'm going to move it to the clock signal, which is placed on 1 Hz. Same circuit. I'm going to turn it back on. Ooh, something is There it goes. Just gotta press down my IC chips. That is one issue I've noticed with this, is that the IC chips, if they're not pressed down properly, will not count. But it is going one by one for the most part through each one. I'm gonna clear it and we'll bring it back. And that is the video. So the mod number for this counter is basically how many states it goes through. It has 1, 2, 3, 4, 5, 6, and it goes down to clear. 2, 3, 4, 5, 6, 7. 7 states. So it's a mod 7 counter. Even though it's not technically counting, it does have 7 states. And that is part number 1. Beginning now with part number 2, we were tasked with creating this ring counter, similar to the Johnson counter, except the input D of A, flip-flop A, is the regular input instead of the inverse input. And some of the presets and clears are connected a little bit differently, which I'm going to explain. But this is my circuit right here. Let me turn it off. I'm going to explain how it's wired right now. So this is my circuit right here. I have two 74 LS74 chips connected next to each other, same thing as the Johnson counter we had for the first part. The only difference that is here for the ring counter, well, there's several differences. So for both of these, the clock inputs for each flip-flop is connected to the clock signal. In this case, I have logic switch A connected, which is later going to be switched to the clock signal. And I have 4 wires coming from that row. Those 4 wires are going to pins 3 and 11 on both IC chips, because pins 3 and 11 contain the clock signal for each flip-flop, with pin 3 on the left IC chip being the clock signal for flip-flop 1, pin 11 on the first IC chip being the clock signal for flip-flop 2, pin 3 on the second IC chip being the clock signal for flip-flop 3, and pin 11 on the second IC chip, the one on the right, being the clock signal for flip-flop 4. Those are all connected to the logic switch and will be moved over to the clock signal later. The difference is a little bit in between this ring counter and the Johnson counter is how the clear and flip-flops are connected. So for this one, the preset and of flip-flop A and the clears of the other flip-flops are connected to switch 1. So preset of flip-flop A is pin number 4 on the IC chip on the left. So pin number 4 on the IC chip on the left, and pin, it's the clears, and pin 13 on this chip. So pin 4 on this chip and pin 13, as well as pin 1 and 13 on this chip, because the other clears are going to be connected to the switch, are connected here to switch number 1. The second thing that makes it different is that the clear of flip-flop A and the presets of the other flip-flops are connected to the VCC. So the clear of flip-flop A, which is pin 1 on this IC chip on the left, is connected to VCC. The clear of flip-flop 2, which is pin 13, the clear, so the clears, my bad, not the clear. So the clear flip-flop A and the pre's of the other flip-flops. So the pre of flip-flop 2, which is pin number 10, is connected to the VCC. Pin number 10 is again connected to the VCC here for flip-flop 4, and flip-flop 3's pin 4 right here is connected to the VCC. That's basically what makes it different from the Johnson counter, including also the fact that instead of the output of the last flip-flop being the inverse connected to the input, it is now the regular output Q is connected to the input of flip-flop A, which is pin number 2. And then the output of flip-flop A, which is pin 5, is connected to pin 12, which is the input of flip-flop B. Pin 9 on this IC chip on the left is connected to pin number 2 on the flip-flop on the right, which is the input to flip-flop 3. The output of flip-flop 3, which is pin number 5, is connected to pin number 13 on this IC chip, which is the input to flip-flop 4. And that output, which is the regular output, is circled back to A. And the positive rail, which is the 5-volt VCC, is connected to the positive rail. They're both jumped together again, the ground coming from the generator. The outputs are connected from left to right to flip-flop A, B, C, and D. Same thing as before. The only thing that were changed were the placements of the pre's and the clears, and how the output of flip-flop 4 is connected to the input of flip-flop A from the regular output instead of the inverse output. So I'm going to turn this counter on, and I'm going to start flipping through. And as I do the clock signal, it's going to just flip a 1 continuously through each LED. And I'm going to now switch it to a clock signal. And I'm going to clear it because it's an active low clear. And it's going to count 1, 2, 3, 4, 1, 2, 3, 4. So it's not really counting as we've already described before, but it is going through several different states. In this case, instead of going through 8 states as the Johnson counter does, since the Johnson counter fills up with ones and then empties out the ones, this one is instead just rotating a 1 through each LED. So this only has the 4 states of mod 4. And the output frequency for each flip-flop is going to be half of the input frequency, which in this case is 1 hertz, so half a hertz, because they're their own flip-flops and they're each connected to the clock signal instead of being asynchronously connected. And that is part number 2.